First of all, let me welcome you. Thank you for coming to the 2015 first seminar for the Water Institute. Great turnout, and we've got a great speaker today. I'm very, very pleased to be able to introduce a long-term colleague and friend of mine from the University of California, Davis. And this is Dr. Thomas Harter. And Thomas is coming back from Germany after spending a month in his hometown, and we managed to catch him through Toronto on his way before he gets back to the weather in California, so we're delighted to have him here. Thomas, just to give you a little bit of a background, is a physically trained hydrologist, studied in Germany, in Freiburg and in Stuttgart, studying with colleagues of ours, including Georg Teutsch, and then after that carried on to Arizona, where he worked as a PhD student with Jim Ye and others, working on hydrogeology and advancing hydrology in that way. And since 1995 has been at the UC Davis, has worked there in the department, if I get the department correct, Land, Air, and Water Resources. And mostly his focus has been on non-point source contamination. He's a trained numerical analyst, has used modeling as a tool for a long time, but merges field work, lab work, and modeling together, as we'll hear a little bit about today. He holds the Robert Hagan Endowed Chair in Water Management and Policy, and that's indicative of the type of work he does. So part of what I've asked him to talk to us about today is how water and policy is merging to handle this massive drought situation in California. So his experience takes him out into the field. He meets with dairy operators. He meets with the farming people. And because of this experience, over 20 years working in this field, he's been leaned on heavily by the government to help them and act as an advisor in the development of the new groundwater law, which is absolutely new, months old. So he's here to talk to us a little bit about that. In 2008, Dr. Harter was awarded the Kevin Neese Award in recognition of this engagement with scientists, engineers, policymakers, so very interdisciplinary skill set. And I'll also mention that he was the main author of the internationally acclaimed study on nitrogen in California, some of which I think we'll hear about today. So please join me in welcoming Dr. Thomas Harter.
Thank you for the wonderful introduction, and I really appreciate the invitation to be here and to engage with your folks and get to know Waterloo. This is my first stint to Waterloo, and I'm happy to have a little bit more winter before I get back into the dry summer heat of California. Well, how about this for an outlook on California and all the fun stuff we do in California? We're going to talk about groundwater today, and I have a little bit of a high flight plan for you to go through. Talk about the drought. Everybody talks about the drought these days, and lucky we talk about drought. We could talk about floods too, which we will eventually. It'll happen again. We'll have floods and mudslides and all that. But give you a little bit about the drought, and then talk about the context. What does it mean? How does water actually work in California? What does the drought mean for us in California? How does groundwater play into that? Understanding groundwater and how it works in California from a 30,000-foot level. And then talk about the policies of managing groundwater from both the quantity and the quality side. But also get back to you and ask the question, what does it mean to you? And why is this important to you? There are some really important connections that I want to make. At the end, the take-home message really is this is a problem, this groundwater management problem that we have in California with its drought is an issue that really is an issue that is important to all of us because of the connection with food and food production. So we've heard this a lot. We've had the drought in California. We've seen a lot of pictures of very dry landscapes, orchards, and other crops going fallow, orchards drying off and dying. People not getting any water in their homes. We have many communities where community water supplies have gone dry. In rural communities, we almost 100% rely on groundwater as a water resource, and where those wells are not deep enough, communities actually have gone entirely dry and are living off of bottled water and truck water for their daily needs. The drought has been around now for 3 years, and we're going into a 4th year. This is a series of maps of California indicating the drought status. This is from the Drought Center, the National Drought Center, and we've been in exceptional drought practically for over a year now, and as you can see, this exceptional drought has, by the end of the summer, had covered almost 80% of California. Some of you may have been at American Geophysical Union meeting in San Francisco in early December, mid-December. We had a deluge of rain from the Pacific. It rained the entire week. We were all very, very happy. We Californians were all very happy. Many of our visitors weren't. But lo and behold, we are back to an extreme drought. It has not rained since the day after AGU ended in San Francisco, and the outlook is not good. There's no rain in the forecast. Our reservoirs are about half as full as they normally are this time of the year, and they're far from being full with few exceptions. But not only our surface reservoirs are empty, the subsurface is emptying out as well. This is from work by Jay Famiglietti working with GRACE satellites, a set of satellites that's measuring the gravimetric, basically the gravity field of the Earth, and doing some interesting manipulations. They can actually estimate at a large scale the depletion, the groundwater depletion over large areas. The last really wet winter was the winter 2010, 2011. This is for the September, November driest season of the year. The anomaly in groundwater storage relative to the 2005-2010 period, which already was a relatively dry period for much of California. We've lost about 15 cubic kilometers of water in those 2 years, and you can add, I'm estimating somewhere between 3 and 5 cubic kilometers to that map just for last year alone. So how does this all fit with our larger water cycle in California? The drought last year, or the drought that's going on, is getting to the point where it is the major drought that we've experienced, certainly in the last 120 years. Last year was the year with the least amount of precipitation, and this graph is not quite correct. It's actually not been the least amount of precipitation measured on a water year annual basis. 1977 and 1924 were actually drier, but if you look at the 3-year cumulative precipitation, in September 2014, we ended at the lowest 3-year precipitation, and it's that longer-term precipitation average that's really important for groundwater reservoirs, because they take a lot longer to be depleted, and they also take a lot longer to be refilled. So if you look at the longer history over the last 110 years, this is the drought, or this is the water year classification for the 2 major streams in Central California, the Sacramento River on the left and the San Joaquin River on the right, where normal is indicated by a normal year is indicated by the yellow bar. Red bars are dry or very dry years, and blue bars are wet years. And you can see we had a sequence of fairly dry years in the 1920s and early 1930s, which coincidentally was the time when a lot of the large water projects we have in California, a lot of the large dams were planned and construction began. We had fairly wet period throughout much of the middle of the last century. Late 1980s, early 1990s, there was a sequence of 5 or 6 years that were dry. And really the last 15 years, with 2 or 3 years exception, have been dry, essentially dry, which with significant consequences for groundwater storage. This winter is not looking good. We had lots of rain in December, and since then nothing. We're now about here, and we're getting to where the driest years were. The projections right now is that in fact we'll be somewhere right here in 2 weeks. There's no rain going out for 2 more weeks, then we'll be among the driest years. We still have a lot of option here in the spring, but it looks certainly more and more like we're dealing with a 4th year of drought. And that has major consequences for many waterworks, because in order for them to get their water 2 or 3 years down the road, they need to make decisions now. And the farmers are making decisions now about what they're going to plant this year in the next 2 to 3 weeks. So from a management perspective, we are dealing with a 4th year of drought in California. The snowpack is not looking very good. The snowpack in the north central and southern Sierra Nevada is at the lowest of any year we've ever been despite the rain that we had in San Francisco. Much of that rain never actually made it all the way to the Sierra Nevada. But there's another aspect when it comes to groundwater that we hear in the news as well, and that is groundwater quality. We have many communities with contaminated groundwater supplies. They're contaminated primarily with nitrate related to farming. And there was a study out just a couple of weeks ago that not only looked at the contamination aspect, but at the consequences of having communities, especially economically disadvantaged communities, with poor water supply, and folks essentially learning that they can't drink their tap water. And kids especially then going to sugary drinks and having to deal with obesity, above average levels of obesity, partly because of the quality of the drinking water. This is a map of nitrate contamination in California, both Central California and Southern California. Fairly widespread excessive contamination of nitrate in groundwater, a problem that we also see repeated in other agriculturally dominated regions of the US. So how does groundwater fit into all of this, and how does the hydrologic cycle fit into this? These are some of the issues. In California, in principle, from a climate perspective, we have a Mediterranean climate. We have rains in the winter, and we have essentially no precipitation except for some thunderstorms over the Sierra Nevada, no precipitation during much of the summer. We have a huge precipitation gradient from over 50 inches along the coast in Northern California to, and some of the mountain ranges, to less than 5 inches in the desert in southeastern California. Most of our water users are sitting in the Bay Area, nearly 10 million people in Southern California, about 20 million people, and then agriculture sitting in the Central Valley in Southern California and along some of the coastal basins in Central and Southern California. That's where your water users are. So we have both a spatial disconnect between where water is available and where water is used. And we have a temporal disconnect between when water is available and water is used, between winter and summer. And what California has done to connect the dots between those is, just here another map before I say that, these olive green colored areas are our irrigated agricultural regions, Central Valley, Imperial Valley, and Coachella Valley, and then the coastal basins, the Salinas Valley being the most prominent one, also Santa Clara Valley. Then we have our urban population shown in these gray areas, mostly Southern California and the Bay Area. Water use for a population that's slightly larger than Canada's population is on the order of 10 cubic kilometers. Agriculture, which is about 4 million hectares, uses between 35 and 45 cubic kilometers per year of water. What we have done to make sure that that water actually gets delivered is we have the snowpack. We have a favorable snowpack, or we have had a favorable snowpack that stores us some of that water that's falling over the winter into the spring and early summer. We have constructed large amounts of dams to store water from winter for the summer, and we have constructed a large network of canals that connect Northern California with Southern California and the Colorado River here at the eastern boundary of southeastern California, with that larger network that goes through California to transport water from the north in the Colorado River to Central California and Southern California. This is the backbone of the water infrastructure that we have in California, and this is only the surface water infrastructure. A central piece in that that I'm not going to talk about today is the Sacramento-San Joaquin Delta, through which most of that water has to go, whether it comes out of the Central Valley, any of these dams that are along the Central Valley east side or some on the west side, any of these dams would ultimately deliver water to this delta and then out to the ocean. This delta serves as the collection point for the State Water Project, which then brings water down to Southern California. It's an ecologically very sensitive area, and we have a huge juxtaposition of environmental issues there with water rights issues. But I'm not going to go into this. What I'm not showing on that picture is the other side of this water infrastructure we have in California, which are the groundwater basins. California consists of, in a very figurative terms, a bunch of bathtubs that are filled with sediments. California is a very mountainous state. You have lots of mountains. Everything that's not yellow here is essentially a mountainous region. This is a geologic map. Many different kinds of formations, but these yellow areas are basin fills. They are alluvial, fluvial, in some cases marine, unconsolidated sediments that are filling these bathtubs with sediments, and that's where most of our groundwater is stored. This is a map of California groundwater basins, which designates all of these bathtub fills, these unconsolidated bathtub fills, with few exceptions up in northeastern California, where in fact some fractured rock aquifers exist in some volcanics. So most of our groundwater in California is groundwater in an alluvial setting. So this is in very simplified cartoon. So you get, here's your bathtub walls. These are the fractured rocks of California. Not that they don't have any groundwater, but the groundwater availability from those fractured rocks generally is much less than what groundwater availability is in these sediments. These sediments have been filled with water via recharge from two sources. One is mountain streams that come off of these mountains, and as they come off of these mountains on these alluvial fans, they very rapidly lose a lot of water and recharge groundwater. But we also have recharge from the land surface, high precipitation years where the vegetation cannot pick up all of the precipitation will recharge this groundwater, especially in Northern California. And now also irrigation water return, where we're irrigating a significant amount of that water, will in fact recharge this groundwater table and get until we essentially have this situation where that recharge then flows down gradient the water table. For those of you that haven't had a background in hydrogeology, basically following the gradient of this water table, flowing into and out of the lowest point in the valley, which typically is a stream. So this is sort of under a natural settings. In the early 20th century, we invented the turbine pump, which allowed us to extract large amounts of water, upwards of 1,000 liters per minute, out of the subsurface, which supports a significant part of our irrigated agriculture, as well as most communities that are sitting on top of these alluvial basins. These alluvial basins, of course, are not homogeneous the way I've just depicted it. They're very heterogeneous systems. There's a lot of characterization that goes into finding groundwater there. There's huge amounts of heterogeneity, which makes for very interesting modeling problems, or makes for very interesting questions to ask in the context of groundwater. This particular graph shows about 10,000 well logs from the Central Valley. This is a distance, almost 1,000-kilometer distance from north to south, and about 70-kilometer distance east to west on average. What we use for pumping for groundwater, and where most of our groundwater management really happens, is in these sands and gravels. And you can see they're only part of this system, and in many parts really only about 20 to 30% of the total sediment column in the upper 600 meters, which is, roughly speaking, the thickness of fresh water in the Central Valley aquifer system. And we see similar thicknesses of fresh water in these much thicker sedimentary basins elsewhere in California, even where the bathtubs are smaller. So we pump water, and we typically pump it because we need water mostly in the summer, less in the winter. We pump in the summer, and we stop pumping in the winter, and this recharge from streams, from irrigation water return, and from precipitation will recover much of the drawdown that occurs in the summer. And we do this back and forth, and it's actually very interesting to take apart the dynamics of that pumping. This is a water budget for a groundwater basin in the south central Central Valley. Let's take a normal year like 1980. We're looking at the water year from October through September, and in a typical water year, above zero, you have the inputs to that groundwater to the root zone of that groundwater basin, and at the bottom, you have sort of the output to that from that landscape. So we put on precipitation in the winter. We get significant amounts of precipitation in the winter that goes onto that landscape. We have surface water in that intermediate blue. The groundwater part happens really in the summer. This is groundwater that's being used primarily for irrigation that's being put on that landscape. And that groundwater is recharged either from streams in yellow or from the landscape in orange, primarily from streams, primarily in the spring months, and then in the summer, we get significant recharge from irrigation. So these two must balance each other out if we don't want to deplete that groundwater storage reservoir. And the balance is between recharging that system in the spring, winter and spring, and then using that system in the summer months. If we get a very wet year, we get a lot of recharge throughout the spring and into the summer with significantly, or some less pumping, not so much in the late summer, but in the early part of the summer, we have almost no pumping typically in a wet year, especially if it's a late wet year. If it's a very dry year, we have a lot of pumping starting in March and April all the way through September with essentially no recharge all year. So we have storage of water from winter, spring months for the summer, but we also have a significant amount of storage from really wet years where we get a lot of recharge but use relatively less for years when we do a lot of pumping but do not get recharge. This is another way to look at this. This is from 2001 to 2010. On the left side, you see water use. On the right side, you see the developed water supply with groundwater pumping indicated in this burgundy color. In a wet year, we have much smaller amounts of groundwater pumping statewide than we would have in a dry year. Typically, about 30 to 35% of our total water supply comes from groundwater. In dry years like last year, estimates are that well over 50%, perhaps 2/3 of our water supply in urban and agricultural areas came from groundwater. So groundwater really is our insurance against drought. That's our bank where we go to go through a drought essentially with very limited economic impacts. And I'll talk about that shortly. In these figures that I just showed here are statewide figures, and you can see there's about a 50% give or take change in the amount of groundwater usage between wet and dry years. In some basins, it's very extreme. This is going back to this basin in South Central Valley, where in really dry years, like 1977, more than half, 2/3 of this water supply comes from groundwater, whereas a wet year, very, very little use is made of groundwater. In fact, most of the water supply will come from surface water. But having groundwater as an insurance allows farmers to essentially grow almost the same amount of crops every year. You see some lower, there's some fallowing and a lower amount of crop consumptive use in wet years like 1977 or in wet years like the 1990 drought, 1988 to 1992 drought. But essentially, the variability on crop consumptive use is much less than the variability we have in annual precipitation in then surface water supplies. But in addition to doing this distribution in time, storing water from a wet year for a dry year, storing water from winter to summer, groundwater aquifers also serve as a huge water delivery mechanism. This is an area in the southern part of the Central Valley consisting of about 30 different water districts. Each district has different surface water rights and as a result also accesses groundwater differently. This district here in the center, Pixley Irrigation District, has almost no surface water rights. And the result is that they're rather efficient with their irrigation because they depend on groundwater. From a recharge perspective, districts that are neighboring this one in the center of this area that have significant access to cheap surface water. They're not as efficient with their irrigations, and they actually recharge a lot of their water through irrigation, both on the north and the south side. And it's these two districts that are actually supplying the groundwater that's being pumped out of the central district. The transfer of water between these two districts and Pixley Irrigation District is on the order of about 0.1 cubic kilometers per year. So these large groundwater basins also operate to balance some of the surface water right distributions, the uneven surface water right distribution that we have in California, and that goes for the entire Central Valley. These are some of the subbasins identified in the Central Valley, somewhat arbitrarily. It's really just one big aquifer system, and you can see that the distribution, the fluxes between these different basins is often on the order of 0.05 to 0.1 cubic kilometers. Fairly large amounts of water that are being transferred between these different subbasins, which also has implications on groundwater management and allocating groundwater rights. So we go back and forth, as I said, and then in a drought, this goes to the point where we have these much steeper declines in water levels, which can be 10 to 15 feet, so about 3 to 5 meters. In some regions, in other regions, it may be as much as 15 meters per year in water level decline because of the imbalance between winter recharge and summer pumping. So when we go through these dry periods, 1977, 1990, early 2000s, and then again late 2000s, each time we've seen these very large, very quick declines in water level in many parts, especially in the southern part of the San Joaquin Valley. Spring 2009 was the end of our drought. Before this one, we had a 2007 to 2009 drought. We've been in drought mode again since 2011. The difference in water level between spring 2009 and spring 2014 in many cases was in excess of 3 meters, and in the southern part of the Central Valley, even more than that. But not only in the Central Valley, other basins as well, all over California, we're seeing these large drops, historic drops in water levels. Changes on the order of 15 to 20 cubic kilometers in storage, primarily focused on the southern part of the Central Valley and some of the southern basins. Here's a longer look at storage in the Central Valley. Looking back to 1920, we've lost on the order of 150 cubic kilometers, and you can add another 20 cubic kilometers for the last 4 years to this number. So we've lost about 170 cubic kilometers of water, most of that focused in the lower third of the Central Valley, where water levels now are often 100 to 150 meters below ground surface. This is the difference in water levels that we have now compared to the lowest ever measured in the 20th century. So including the 1977 drought, including what was going on in the middle of the century when we didn't have these big water projects, but we did do a lot of groundwater pumping. And you can see that even going back to those low water levels in the mid-20th century, we're now significantly lower, on the order of 30 meters and more in some cases, in terms of water levels in these large alluvial basins. Every red well on here is a well that is at the historically lowest ever measured level. And that doesn't include, we have many areas for which we actually don't have data. These are all these brown areas. We don't even have data to look at that. So what does that mean? Well, the immediate impact is that anybody who has a well has to spend more money for pumping. It is estimated that last year alone, agriculture spent $500 million extra in pumping cost over 2013 because of the lower water level in 2014 compared to 2013. I will talk about land subsidence, water quality. I'm going to skip seawater intrusion today, but that's another significant complication. And I'll talk a little bit about surface water depletion and impact to groundwater-dependent ecosystems. Pumping costs. And then there is drilling cost. We have many wells falling dry. There are no official numbers for how many wells have gone dry in California. We have on the order of 250 to 500,000 domestic wells. Many thousands of these have gone dry. We have some numbers that indicate that at least on the order of 2,000 wells have gone dry last year, meaning you have a domestic well owner who has no access to water other than bottled water or through a neighbor. We've seen large increases in well drilling in the last 2 years. We've seen some high well drilling numbers in 2009 because of the previous drought. overall throughout California, not just in Central California. We've seen several hundred new wells drilled in each of the county. I'm estimating that we've probably drilled somewhere between 1,500 and 2,000 new agricultural wells, irrigation wells, and probably at least that many new domestic wells, at a cost of anywhere between $20,000 and $2 million, depending how deep you go, in each. Overall, the impact to agriculture is estimated to be on the order of $2 billion, $1.5 to $2 billion, to the state economy on the order of $2.5 billion. That's a relatively small drop in the bucket for the state overall, but the regions that are focused on agricultural productions, and especially in the southern Central Valley, that's a very big hit. Unemployment rises, unemployment increases are on the order of about 20,000 jobs. We've lost about 5% of the irrigated area last year. That has basically either gone fallow or where we lost the permanent crop. Prices, interestingly, have, at least economists say that prices were not impacted by the drought. The high prices we have for many of the crops that are grown in California, almonds, wine grapes, vegetables, are actually more because of increases in demand and not so much because of the crop losses. In fact, the crop losses are not that large on many of these specialty crops, at least not at the moment. One of the economic consequences that's very important is not included in many of these numbers, and that's land subsidence. That's something we're only beginning to look at. Land subsidence was a big issue in the Central Valley when we first started pumping in the 1930s and 1940s and didn't have the big water projects yet. And I showed you earlier the drought in the 1920s and 30s was quite significant. We've had land subsidence in some areas in the Central Valley that exceeded 10 meters. Now 10 meters, that is a lot in a landscape that is as flat as this here. This is Arne Poland, who's a geologist with the US Geological Survey back in the 20th century and who's been a pioneer on doing a lot of the land subsidence work, in a famous photo that he took in the San Joaquin Valley where he's showing the elevation of the land in 1925, 1955, and 1977. That's astounding to have the Earth's surface altered by this much simply because we're pumping groundwater. And we're doing this again. This is GPS data from the last, this is from the drought between 2007 and 2009, where we've seen about, let's see, this is about 20 feet. 10 feet, about a meter per year in subsidence. No, it can be quite that much. It's less than that. Vertical displacement in feet, so that would be about 10 centimeters here. Last year, we've seen a significant amount of subsidence in areas both in the southern part of the Central Valley as well as in the central part of the Central Valley. All of these red and orange areas are still subject to land subsidence, and a lot of these are urbanized. This is land subsidence in the southern part of the Central Valley just between May and October last year. In some areas exceeding 25 centimeters in 6 months. 25 centimeters in 6 months across these large swaths of land. Land subsidence here is primarily due to clay layers that are interfingered between sand and gravel layers. Clay layers collapsing because of the lack of hydrostatic pressure. So land subsidence is a big issue and potentially associated with large costs. We have large, for example, large canal systems going across this landscape, and with these amounts of land subsidence, all of them would have to be regraded at very large infrastructure costs, infrastructure maintenance costs. Another cost is to the environment, especially sort of at that groundwater surface water interface in more mountainous regions of California. Seepage out of springs has been reduced as a result of the drought. That impacts many areas in the mountainous regions in California. Wetlands have been impacted. We have many seasonal wetlands that are wet in the winter but then dry out in the spring and have specialized flora and fauna associated with them, and then are entirely dried out in the summer naturally. Many of these vernal pools have been of limited extent or non-existent during the drought. Now, some of these vernal pools are completely isolated from groundwater. They're essentially little tubs that receive water that collects in them, but the subsurface is too impermeable to really infiltrate. Many of these pools are directly connected to the groundwater table, and use of groundwater will also impact the viability of these wetlands. Very big concern, especially in the central part of the Central Valley, which is the lowest part of the Central Valley. And then, of course, as we draw water down further, we have this disconnection that happens from streams. But even before these streams get completely disconnected from groundwater, simply lowering the water table by pumping near a stream will actually reduce the amount of base flow going into the stream. Now, this is sort of a delayed effect, and the further away the swell is, and the lower the hydraulic conductivity here, the larger the hydraulic conductivity and the larger the storage coefficient in here, the longer the delay between when pumping in this well will actually impact that stream. But similarly, the longer the delay between when that pump stops pumping and when the stream stops leaking towards that cone of depression that the well has created. So we have significant impacts between groundwater pumping and surface water throughout California, but again, primarily in those regions that actually still have an extensive groundwater surface water connection. Many parts in the Central Valley, in the southern part of the Central Valley, we've lost that connection 20, 30, 40 years ago already. So what has California done about all of these problems? How are we going to get a grip on these issues? And I'm going to speak here exclusively from a groundwater perspective. On the surface water side, we have surface water rights since we've had surface water rights from the beginning of statehood, and we have a state agency that manages surface water rights since 1914. On the groundwater side, we don't have any water rights that are written down by an agency and that I can go get when I want one. It's essentially been handled on a common law basis, meaning everybody does what they want until they're dissatisfied, and then they have to go to court and fight with their neighbors in court about it. And the courts have a legal system to divide up water that's primarily based on what's called the correlative rights doctrine. In California, the correlative rights doctrine is the governing principle by which courts will divide water. And it essentially says that if I own a piece of land, then my right to groundwater is correlative to the size of my parcel relative to everybody else, correlative to the property of the aquifer underneath my parcel relative to everybody else, and it's a right to the safe yield of that groundwater basin. It's not a right to deplete the groundwater basin at will. It's a right to the long-term safe yield of that groundwater basin. We've had that correlative rights doctrine for 100 years. We have a mandate for beneficial use. We have created many special districts, primarily for irrigation and water distribution of surface water, but these districts now often also get involved in groundwater and groundwater management. We have some districts that were specifically created to do groundwater replenishment. Counties in California have, under their police power, the right to curtail exports of groundwater out of the county. And we have a number of counties that have actually exerted that right last year and explicitly created policies to prohibit export of groundwater out of their counties. The courts, of course, are always the ultimate place to go if people fight over groundwater. And when courts get involved with a larger groundwater basin, that usually means that the entire basin is being adjudicated. Adjudication refers to a court process by which the courts basically try to find all the major landowners. They try to get expert testimony on how the groundwater basin works and have everybody divide up the available safe yield among the various landowners and water users in the basin. And many of the Southern California groundwater basins, or many of the subbasins, have been adjudicated early in the 20th century when those smaller basins experienced rapid amount of drawdown in water table and overdraft. Some of these adjudications are still pending. and ongoing. But they're limited to Southern California, which has the smaller groundwater basins, something like the Central Valley. We haven't seen the adjudications because basically we've been pumping and pumping and pumping and pumping. Now, just a quick, couple quick examples. We have the Water Replenishment District of Southern California as an example of a district specifically created to manage a groundwater basin, not as much on the extraction basis, but manage it on the replenishment basis. The replenishment district actually raises taxes from pumping fees to manage recharge into this basin just south of Los Angeles, partly to make sure that there is sufficient water supplies for the municipal wells in that basin, partly to actually prevent further seawater intrusion. They had drawn down their water table well below sea level in the early part of the 20th century, and they were quite successful in raising water levels, and especially near the coast water levels, to prevent further seawater intrusion. This is another example from the Santa Clara Valley. This is basically the southern end of the San Francisco Bay, what's also known as Silicon Valley. Santa Clara Valley, partly because of agriculture, experienced rapid drawdown in groundwater levels in the middle part of the 20th century, with accompanying lowering of the land to levels well below sea level in San Jose and Santa Clara. And through building local reservoirs and capturing more local water before it ran off into the ocean, and the buying up deliveries of water from the State Water Project, they've been able to reverse their groundwater level decline over the last 30 years substantially, and have kept their land subsidence in check as well. So these are two examples of managing groundwater conjunctively with surface water, specifically to arrest this decline in water levels. And both of these examples would be managing groundwater locally, where you have local water, you may be importing some water, and you basically store water in wet years for use locally in dry years. So you have these variations that are, again, going back to this groundwater basin being used as a bank. We have outright groundwater banks that import water from somewhere to then export it somewhere else. There's some groundwater banks in Southern California storing upward of about 0.5 cubic kilometer per year. And the largest water bank is the Kern County Water Bank in the southern part of the Central Valley, where we're storing about 4 cubic kilometers of water that's been built up over the last 20 years, also for export to Southern California. And the depletion of the southern part of the Central Valley that you saw in the pictures that I showed earlier doesn't actually account for the fact that some of the water that's in there is stored in there for sale, for delivery sometime to Southern California. It's actually part of a bank and needs to be taken out at some point. Groundwater management is done by infiltration basins, wetlands, or outright injection. Also, aquifer storage recovery is a big part of this, and there will be a lot more of this going on as we go forward into the future. One of the projects that I'm involved in is using groundwater banking for environmental flows. In this small basin in Northern California, we have salmon in the local stream that come up from the ocean. The stream is almost dry in the summer, and we're trying to increase summer base flows by having less groundwater pumping in the spring along in this agricultural region, and instead using surface water while it's still available from the snow melt off of this mountainous watershed. There's no surface water storage reservoir in this watershed, and we're using essentially the groundwater aquifer here as a storage reservoir for that snow melt to then be available for summer base flow. And we're currently doing some modeling to figure out how much we can actually increase summer base flow in that stream using some of these groundwater banking approaches in the valley. Now, in terms of the larger groundwater management, none of that has happened entirely in a vacuum. We've had state action on groundwater management for about 30 years now. And interestingly, the state action comes primarily at a time when we have droughts. The 1990 drought brought the so-called AB 3030 legislation in 1992, where the state said, locals, please do groundwater management, do something about your problem. We'll help you a little bit. We give you some technical guidance. I don't think there was financial resources made available at that point. That happened in 2002 at the end of the next drought when Senate Bill 1938 was passed, and the state said, okay, we don't want to get into your business of groundwater management, but if you want money from us for your water projects, you better have a groundwater management plan in place locally. And there was that legislation then led to the development of some minimum guidelines for what a groundwater management plan actually had to entail. The earlier groundwater management plans were anywhere between 2 pages for some basins and 200 pages for other basins. We had fairly little action since 2002, but the current drought has prompted the legislature to pass the Sustainable Groundwater Management Act of 2014, which went into effect 4 weeks ago. And it is in the opinion of many California water experts, the most significant water legislation that we've had in California on the water quantity side since the 1914 Surface Water Rights Act was established. And it's the most important water legislation since we passed the equivalent of the Clean Water Act in the late 1960s. So what does the Sustainable Groundwater Management Act do? Well, first of all, it actually explicitly now states that the goal of the state is to have groundwater resources be managed sustainably, not as a resource to be extracted, but to have it managed sustainably for long-term reliability and multiple economic, social, and environmental benefits. So sustainability is playing a major role in actually trying to figure out what that means. And the legislature said, well, sustainability means that we don't have undesirable results. And then they actually go on to define what these undesirable results are. Well, undesirable result is one of the following: a chronic lowering of water levels, which is equivalent to a reduction in groundwater storage, seawater intrusion, degraded water quality, land subsidence, and surface water depletions. This is actually interesting. Of these, many we've been dealing with indirectly in the past, but this is the first time that we explicitly acknowledge groundwater as being connected to surface water. The legal system actually does not know the connection between groundwater and surface water. They treat these two systems as completely separate. So this will be interesting, and this is probably where we may have the biggest changes in practices over what we've done thus far. So the goals of groundwater management from this act going forth will be to enhance local management, to establish minimum standards on how this management actually has to happen, to provide agencies with the authority, but also the technical and financial assistance to put them in a place where they can actually actively manage their groundwater, to avoid these undesired results, to improve data collection and understanding. A big problem we have in California is that we have a lot of data in a lot of different silos that don't talk to each other. And even if we were to put all of them together, there's a lot of data that we would like to have, but that don't exist. Lots of work for hydrogeologists and hydrologists here. Increasing groundwater storage in groundwater banking activities. Stanford has recently published some results that estimate that groundwater storage, expansion of groundwater storage reservoirs is about 1/3 of the cost of building surface water storage reservoirs. All without a whole lot of state intervention. One of the biggest things in California is that nobody really wants the state to come in and tell them what to do. I imagine that's maybe not that different in Canada as well. And the idea was to provide locals with the opportunity, but also with the tools to do this, and say, we'll give you a certain amount of time, and if you can't do it in that amount of time, then the state will step in. So the first step will be within the next 2 years for these local groundwater basins to establish a groundwater sustainability agency, or short GSA, and Those agencies need to cover all of these medium and high priority groundwater basins that we already have identified in California, about 100 of the 500 groundwater basins covering about 90% of the groundwater extraction. This will be a huge task to have all of these basins covered with some form of a groundwater sustainability agency. This is a map of the existing groundwater management plans, which as of the first of this year are actually no longer valid in terms of a legal groundwater management tool. All of these groundwater management plans will have to be converted into a groundwater sustainability plan. Even the existing groundwater management plans only cover about half of the basins that will need to be covered in the future, with quite more rigorous implementation guidelines. Under these existing groundwater management plans, we do have typically, what these plans have done is they have done basin descriptions, they have provided some context. We have agencies involved, we have stakeholder groups involved, we have often a groundwater advisory committee. There is some monitoring of groundwater levels ongoing under these groundwater management plans, at least some of them, not all of them. There is a limited amount of accountability and review. Actually, there has been no mandate to review these groundwater management plans on a regular basis. So the Sustainable Groundwater Management Act will go a significant step further over these existing groundwater management plans, in that the accountability and review part will be an essential part of it. It gives local agencies a mandate to enforce their plan. They can do demand management. They can tell a pumper to stop groundwater pumping if that's what they choose to do. The Act encourages the integration with both surface water management, but also with water quality management. It encourages that groundwater planners and managers actually talk to land use planners, and that there is a regular exchange, at least of information. Decisions do not have to be tied together, but at least the information flow between water managers and land use planners has to be there, demonstrably so. So after these groundwater sustainability agencies are formed, we need to have these plans within 5 years of formation. The plans will include governance structures. Stakeholders will be involved in making these plans. As I said, collecting information will be a very critical part of this. And the most critical part will be this groundwater management portfolio. And the kind of things that these agencies will do and be engaged in to actually arrest water level decline where that occurs. That may be limiting extraction, that may be reducing the extraction, or cutting it off entirely. Or, on the other hand, increasing the amount of recharge that occurs in these basins. And there's a lot of creative room for figuring out how we can use the mostly agricultural landscapes of these basins for recharge, additional recharge. Conjunctive use of surface water and groundwater will be expanded. I think groundwater banking will be a very big part of this. And then after 2020, or after 2022, these agencies will then be in charge of actually implementing these plans with 5-year checking points. And if they're not able to actually implement it as planned, or if they're earlier not able to actually put a plan together, at that point, the threat is, and what makes this whole thing work, hopefully, that the state will step in and at least temporarily take over a groundwater basin to establish these sustainability plans. So that's on the groundwater quantity side. I mentioned earlier that we have significant issues with groundwater contamination. We have some counties where more than 40% of domestic wells are exceeding the drinking water limit for nitrate. We have a huge imbalance between the total amount of nitrogen going into the agricultural landscape versus the amount of nitrogen here in green taken up from that landscape, leading to this pollution, among other sources. And if we don't do anything about this, we're likely to increase the percentage of wells that are impacted significantly over the next 20 to 30 years. This is one of the results that came out of our nitrate studies. Water management and nutrient management both need to go together to actually improve the situation, and to the degree that it is irrigation management that is really the key driver for the losses of nitrate to groundwater, managing water quality in groundwater is tightly linked to managing water quantity. From a nitrate perspective, we want less recharge because we don't want nitrate to percolate into groundwater, which then impacts the amount of recharge that goes into basin and impacts how much groundwater we actually have available. So quality and quantity management are intrinsically linked. We have done a lot on water quality management over the last 40 years. We've regulated point sources, we've regulated surface water, but we have not regulated in the United States or in California, regulated non-point sources of groundwater pollution. I bring this up because this is something that doesn't seem to kind of get on the radar for many people, but it is actually a completely different area of groundwater management and regulation from regulating point sources. Non-point sources cover millions of hectares as opposed to a 1 hectare or half hectare site. Their intensity may be not as high, but as opposed to an industrial contaminant site, the contamination occurs as part of the operation. It's part of the regular recharge as opposed to an incidental leakage. And so it happens regularly or seasonally, and it happens across the landscape in various amounts. This poses a completely different challenge to designing monitoring systems on who is putting how much into groundwater, designing management systems, and doing assessment on how we manage and remediate and treat groundwater pollution. Where we're going with this in California at the moment is, rather than enforcing groundwater pollution based on monitoring wells that are sitting down gradient from each individual site, which we can't do on 4 million hectares of agricultural land. We can't put monitoring wells down gradient from each individual field. Where we're going is what I would call a 3-track monitoring approach, where we're actually monitoring management practices rather than groundwater quality. And we're monitoring management practices as a proxy for monitoring groundwater quality, which means we need to do research that will link that proxy monitoring tool to the actual impact to groundwater, which by law needs to be measured. And instead of groundwater monitoring underneath every field, we are charged with developing regional trend monitoring networks that will capture, at least with some statistical significance, actual trends across the landscape, and hopefully also with respect to the different sources that we have within that landscape. Again, a very large area where we can do research. Besides the science needs to do this, for regulatory agencies, this is a huge challenge because they're operating already with pollution, but under templates that don't fit into this non-point source. And for agriculture, this is a huge change in their practices and in the way they think and operate that will take at least 1 generation to adjust. Let me close with a comment on where this story goes beyond California. California is not the only place that grows food that we all love to eat. In California, we grow a lot of foods that are almost exclusively grown in California, and so we can't stop having agriculture in California. In fact, we can't stop doing agriculture in a lot of places that are as dry and hot as California. 20% of the agricultural land on this planet is irrigated. But that 20% of agricultural land that's irrigated produces almost half of our food. 40% of our food comes from irrigated lands in semi-arid and arid regions. Some of those mine water, some of those manage their water. These are the biggest water users on the earth, and you can see that includes China, India, Southern Europe, and the United States, as well as Brazil. Much of that is for agricultural uses. Agriculture in many of these countries is 80% or more of the groundwater use, of the water use, with a significant part of that water coming from groundwater. And even if it's not the entire, even if not all water comes from groundwater, in all of those regions, groundwater resources function as the insurance for years when we have drought. Groundwater is essentially the bank where farmers go in India or China or California when surface water is running out. And for the older folks that are sitting in the room, I remember when I was a kid, we had famines, not just in Africa, but we had famines in Asia and elsewhere. All of that has gone away, except Africa, which is the only continent that doesn't have significant groundwater development. And that's to show the significant link between global food security and how we're managing our groundwater basin. We've done huge developments in these countries, China and India, to do groundwater development over the last 50 years. And the result has been, not just in California, but elsewhere as well, rapid declines in water level. On top of that, we have, in those same countries, large excess of nitrogen, leading to nitrate pollution in most of these agricultural regions. And while these regions may not cover the entire globe, if I actually draw this map so that it's proportional to the population that these agricultural regions support, the map looks more like this. And now it becomes much more clear why our ability to manage groundwater on both the quantity side and the quality side in places like California has important consequences for our global ability to provide sufficient food to feed a world that will be exceeding probably 10 billion people within the next 40 years. With that, I'm at the end of my line, and we can open this up if we have time for some questions.
So we're a little bit late, folks. If you have to leave, that's fine. But if you have some questions, let's take advantage of having Thomas here to address your questions. Start right at the back there.
With your, the sustainability plans that have to come up by the local government, is that tied to, the actual geological basins, the hydrological basins? It seems like you really need to have a plan for the entire basin there. How can you work that up without there being overlapping issues of, well, we can't balance it unless we talk to our neighbors?
That's a great question. We struggled with that. The legislators struggled with that last summer as they were discussing how this thing looks like in detail. And a lot of the backroom discussions were about, are we going to require a single agency for each basin or designated sub-basin, or can we allow for multiple agencies? And because of the political realities in California, the decision was made to allow for multiple agencies, that is also for multiple plans within a sub-basin. So even the sub-basins, which are already dividing up the larger basin, which the largest one being the Central Valley, but even within sub-basins, designated sub-basins, there is an allowance for having multiple agencies if that is the case, but they have to communicate with each other, and they ultimately have to be able to show that the total of their plans will be workable for groundwater sustainability goals. They have to coordinate. The communication is prescribed by the legislature. How that has to look like in detail, and where the agencies in charge of overseeing the development of these plans and the approval of these plans, where they could draw the line, that is part of a process that will occur over the next 2 years. The Department of Water Resources and the State Water Resources Control Board are the two agencies that have been assigned the implementation of the act, with the Department of Water Resources being the agency that sort of does the technical assistance and the planning and also develops the technical regulations, and the State Water Board being the COP, more or less, that steps in if the Department of Water Resources decides that a plan is not being implemented properly, or that a plan has not come together properly. But these technical guidelines still have to be developed, and we will see a lot of discussion in the next 2 years about exactly what needs to be done when you have multiple groundwater sustainability agencies within a sub-basin, and how they actually figure out what their sustainability goals are.
And then we'll go to Ed.
Thank
That is a great question. I think from a population perspective, in my opinion, there's a lot of room for growth. We have not increased the amount of consumptive use in our urban areas, as far as I know, over the last 2 to 3 decades, despite significant growth in population, largely because we have been able to decrease the per capita amount of water being used, both for homeowners as well as in the industrial, on the industrial side. Even for agriculture, the water efficiency of agriculture has actually increased. They have been able to grow a lot more food, fiber, and feed for the amount of water they are using. But from a groundwater perspective, what that means primarily is they have been able to apply their water better and with better timing so that the water actually goes into the crop and no longer leaches into groundwater, which is positive from a water quality perspective, but of course has consequences for the way we manage the quantity of groundwater. And that's where we have to set in with really creative solutions to make the system go from inefficient irrigation to efficient irrigation with less leaching of farm chemicals, plus clean groundwater recharge on top of that within that same landscape.
I've heard rumbling rumors in the past about California building a canal or a big pipeline under the Canada.
Oh, it goes further than that, Ed. It goes all the way up to Alaska. There's a beautiful movie out there that it looks like a promotional movie. I don't actually know how it came about, that details exactly how we would bring water from Alaska through a series of 56 or something like that reservoirs that were to be built along the Cascade Range between Alaska and California. There was a plan, as far as I know, there was a serious plan put on the table in the 1950s or 1960s, but I'm not aware of any serious rumbling. We can't build 2 tunnels under the delta. We will not be able to build anything to Canada.
My other question is, your changes in groundwater storage, so the number of graphs were very dramatic, estimated, I presume, from changes in water level records.
Yes.
How does that compare to Jay's GRACE estimates?
Yeah, so Jay Famiglietti has actually made it a point to show that his estimates are very closely following the estimates that have come out of the USGS groundwater modeling efforts that Claudia Font has led with a Central Valley hydrologic model. They're coming out for the same period of time. GRACE has only been in operation since 2003, I believe. So for that period between 2003 and 2009, I've seen some graphs where he's showing that the GRACE estimates are similar to what the modeling estimates are. I have not seen any estimates that were based directly on water level, on drawdown measurements, essentially. I believe that the estimates that I showed, I'll take that back. The estimates that I showed from the Department of Water Resources that show changes in storage, they're based on their water level data, not on their modeling data. Which always goes with the storage, with the specific yield, and getting that specific yield down to some kind of accurate number, and that's the most difficult part. For a lot of these discussions that we'll also have with respect to long-term sustainability, estimating what the specific yield is and relating past numbers to future volumes is going to be critical.
Because there's also issues with GRACE data, how you do certain corrections.
That is right. So GRACE is also not necessarily, there's some uncertainty about those estimates as well.
2 more quick ones. Yeah. Go ahead. Hold on 1 second.
Are there any wide-scale remedial measures being taken to improve the water quality in the state?
Yes. So the question is, are there any wide-scale measures being taken to improve water quality? The regulatory approach with this 3-tiered monitoring system that I mentioned at the end for the United States is actually unique. The Clean Water Act that we have in the United States since 1972 is actually exclusively concerned with surface water quality. There's no Clean Water Act for groundwater. In California, we actually passed a Clean Water Act called the Water Quality Control Act 3 years before the federal Clean Water Act was passed. It's actually referred to, our Clean Water Act is referred to as the Porter Cologne Water Quality Control Act. And the California version of the Clean Water Act, partly because it was actually established 3 years earlier, explicitly included groundwater as a water body and in principle allowed for the state to regulate discharges not only into surface water but also into groundwater. Initially, groundwater discharges from non-point sources were essentially being exempted from having to get a permit, the way a wastewater treatment plant would receive a permit on its discharge. Those waivers were taken away in 2002 by legislative actions. And the regulatory agencies in charge of giving out water quality permits and doing all of the water quality planning and assessment are undergoing major are implementing major new programs to control both nitrogen pollution of groundwater from various sources as well as salt pollution. The programs initially started in 2007 when we passed the dairy order for the Central Valley, which holds most of California dairies and the largest amount of the confined animal facilities that we have in California. Was the first major legislation that would actually prescribe management practices and monitoring tools for an entire agricultural industry. We're currently in the middle of implementing what's called an irrigated lands regulatory program in most of California's irrigated agricultural lands that will also have some form of this 3-tier monitoring system. And there is a third effort underway to look at salt and salt inputs to groundwater in the Central Valley. And just last year, a feasibility study was implemented to estimate what kind of desalination would have to be worked out to not have groundwater in the Central Valley be degraded through salinity increases further over current levels. And the estimates, the initial estimates for the cost of desalination are on the order of $2 to $4 billion annually. So yes, so the regulations is really what's happening, and that's unique for the United States. We don't have that elsewhere in the United States to that extent.
Last word on.
Do you see any relationship between these persistent droughts and climate change? Those predictions say that the dry areas will get drier, wet areas get wetter.
There is a lot of talk, and there's certainly a lot of concern about climate change. The Department of Water Resources and the state government have made that, and even also previous governors have made that a priority, looking at potential impacts from climate change to the degree that we can predict those. And the planning efforts are now certainly going into a direction where potential for climate change is being taken into account. The biggest change in California will be, no matter which way it goes, but the biggest change will be a decline in the snowpack because of earlier snowmelt, and there are a number of planning efforts underway. I don't know the degree to which this particular drought, and I don't know anybody would know whether this particular drought is part of climate change or not. We certainly have had droughts in the past, and we've had longer droughts in the past. We've had 50 to 80 year drought periods. As we can show that we have had those in the 9th century, and we've had those again in the 12th or 13th century. Significantly longer droughts than the ones we've seen in the last 120 years.
Okay, with that, I think we'll just finish up. Just two final things. Just on behalf of the SWIGs, I just want to remind you that there's a reception with Thomas up at the Grad House starting at 4. Make it over there. Please join us. Apparently there's free food, some of it imported from California. We'll use some of their food. And secondly, Thomas, thank you for a wonderful talk. The way California figures this out will impact the world. So thank you for doing that, and here's a token of our appreciation.
You're entirely welcome. Great. Thank you for having me. Thank you.